Good morning all. In the last class we have discussed the classification of phase diagrams, and the first classification unary phase diagram, second one the binary phase diagram, ternary and quaternary phase diagram, and we discussed the unary phase diagram and also the first special class of the binary phase diagram, which is the binary isomorphous diagram. In this class we will be discussing the second classification of the binary phase diagram, which is the eutectic phase diagram. When we speak about the binary phase diagram, binary isomorphous phase diagram, we told like it is the special class of phase diagram in which the two components, which is forming the solid solution or forming the alloys, it will be completely soluble in its liquid state as well as in its solid state, which means above the melting point at its liquid or the molten state it will be completely mutually soluble, and when we are solidifying it below its melting point it will again be in single phase or solid solution. Okay, and normally all the material or all the alloys, the components will be soluble in its liquid state, which means above its the melting point all the elements in the alloy will be mutually soluble. But once we are cooling it below the solidification temperature, normally in many alloys the solubility limit will be restricted and it will be precipitated out of the material as intermetallic or precipitates. So in this particular class of phase diagrams or the eutectic phase diagrams, we will deal with the alloys which have complete solubility above its liquid state, but which is having restricted solubility or limited solubility when we are cooling it below the solidification or melting temperature. So the eutectic systems will not be having complete solubility in its solid state. So it can be further classified into two, where the first classification comes as the components which are completely soluble in liquid state and completely insoluble in solid state, which means above the melting point it will be having complete solubility, below the melting point it will be completely insoluble. That is one class. Second class is the components which have complete solubility above the liquid state but have some solubility or limited solubility in its solid state. That are the two classification of eutectic systems. Okay, and the word eutectic actually means it is easy to melt, which means at a particular point called as a eutectic point there will be a corresponding temperature as well as corresponding composition for that particular alloy, which will be having the minimum melting point. Okay, so at eutectic point the whatever be the alloy or the whatever be the composition of that particular alloy, that particular composition will be having the least melting point. So at eutectic composition we can easily melt, so it is called as that's why it is called as easy to melt. Okay, so the word eutectic actually means it is easy to melt. And when we are considering the eutectic reaction, when a liquid solid solution of a particular composition solidifies at a particular fixed temperature, which is the eutectic temperature, two separate phases are formed, and that particular reaction is projected, which is the liquid at eutectic temperature. Once upon solidification or cooling, it will be converted to two separate separate solid solution, which means it is not a direct transfer from liquid to single phase solid, but a liquid is transformed to a two phase solid, which means it will be having two separate phase solid. First, that's why it is represented as alpha solid solution and beta solid solution. So a single phase liquid is transformed to a two phase solid. So I have already mentioned like eutectic point is the point which is corresponding to a particular temperature and a particular composition at which the liquid will be having the lowest melting point. So we can say always an alloy of a specific composition which solidifies at a specific fixed temperature which is lower than all other composition, which means the particular composition and particular temperature combine to form a particular point which is the eutectic point, and that particular point will be having the lowest melting point among all other composition of that particular alloy. In the figure you can see the eutectic point corresponding to a particular phase diagram of an alloy. In that figure you can see the liquidous line, which is the boundary which separates the solid plus liquid phase the first liquidous line which separates the alpha plus liquid phase from the liquid state, and the second solidus boundary which separates the beta plus solid state from the liquid state. So this meeting point of these two lines, these two liquidous line, you can see at a particular temperature which is marked as the eutectic point. That particular point, you can see it has the lowest melting point, which means if we are solidifying that particular material or particular alloy at that temperature, it will be melt at the significantly lower temperature when comparing to the region at the left side as well as the right side. So that particular composition at the point eutectic point and that particular temperature at the eutectic point together constitute the eutectic point, and the whatever be the alloy it can be easily melted at that particular point. That is one important fact. And the another fact which I told is we have mentioned that particular reaction which is the eutectic reaction, where the liquid directly transforms to a two-phase solid. Or the figure you can see at that particular eutectic point, if you are directly cooling the material above the eutectic point, you can see it will be existing as the liquid above the eutectic point. At any temperature it will be existing as the liquid state, and below the eutectic point you can see it will be directly converted to alpha plus beta. Alpha plus beta actually represents a two-phase solid solution. So liquid to direct two-phase solid solution transformation, it takes place at the eutectic point, which is the eutectic reaction. So as we mentioned, in the case of eutectic phase diagrams, there will be limited solubility or below in the solid state. So in the case of binary isomorphous diagram, we have the complete solubility in the solid state, but in the case of eutectic phase diagrams, we will be having the limited solubility. So it can be further classified into two. The first classification is the components which are completely soluble in liquid state and have limited solubility in the solid state. One well-known example is the silver copper phase diagram. So here the silver as well as the copper will not be completely soluble in the solid state, but will be soluble up to a particular limit. So that's why we will be having the region of a two-phase solid solution, which is the alpha plus beta region. So if you are considering the phase diagram, we can see similar to the isomorphous diagram, during the construction we will be having the complete pure elemental silver at the extreme left side and pure elemental copper at the extreme right hand side. So next we will be marking the melting point of the silver, which is 962 degrees centigrade. We will be marking the corresponding melting point of pure copper, which is 1085 degrees centigrade. The y-axis actually represents the temperature, and over the x-axis we can see the weight percentage of element B, which is the copper. Okay, so extreme left position we have silver, so we will be adding copper to the silver in varying concentrations, such that when we reach the extreme right position we will be having 100% copper and 0% silver. So we will be making the alloy in such a way. Now we can see at higher temperature the all the elements, the copper as well as the silver is completely mutually soluble. We cannot separate this silver and copper distinctly. Okay, and it will be having complete mutual solubility. So we can see it exists as a single phase liquid. So that's why like we have a single phase liquid, a same color throughout the entire temperature range at higher temperature, entire composition range at the higher temperature. So but once we are cooling down, we can see the solubility limit of the both is getting restricted, or it is getting decreased, and it will be having a limited solubility. You can see two single phase region, which is alpha as well as the beta. You can see alpha is a single phase solid solution of copper in silver. We can say silver will be the parent material in which we will be having a limited solubility of copper, and the maximum amount of copper which can be accommodated or which can be dissolved in silver is very much less than 10 weight percentage. The maximum limit you can see, which is corresponding to some 779 degree centigrade. So at 779 degree centigrade, the silver can accommodate a maximum of less than 10 weight percentage copper. So alpha is a single phase solid solution of copper dissolved in silver. Okay. Similarly, if we are considering beta, again beta is a single phase solid solution. Beta is a single phase solid solution of silver in copper. Okay, if we are considering the case of beta, again the maximum solubility limit of silver in the copper, it is less than a 10 percentage. So you can see more than 90% it will be copper, and silver will be less than 10 percentage. So beta is a single phase solid solution of silver in copper, where the maximum solubility limit occurs at 779 degree centigrade, and it is even less than 10 weight percentage of silver. Then we have in a majority of areas which is alpha plus beta region, which actually means it is a two-phase solid solution. We cannot say it is a single phase solid solution. It consists of two phase. So it will be showing the properties of alpha phase as well as beta phase, and how these alpha and beta phases are arranged, it depends upon the microstructure of the material and the other microscopic features. But we cannot say it will be having a homogeneous properties of a single phase solid solution, but it will be like a precipitates, okay, of either alpha in beta or beta in alpha. Okay, so the majority of region, it is a two-phase solid solution, and that is the reason we will call it as a example for the eutectic phase diagram with a limited solubility in the solid state. Okay, another important point is the eutectic point. You can see the eutectic point where we can observe the minimum melting temperature. So the eutectic point in this particular phase diagram, it exists at 779 degrees centigrade, and the eutectic composition 779 degree centigrade temperature, and at a eutectic at a composition of less than 30 percentage of copper in silver. Like we can say the atomic percentage of copper corresponding to the minimum melting point of the liquid state, it is closely to 29 degrees centigrade. So we can say that 29 percentage of copper. So the eutectic point exists at 779 degrees centigrade and 29 weight percentage of copper. Okay, at that particular point, if you are directly transforming from liquid to solid state, we can say at a lower temperature we can convert the liquid state to a two-phase solid or alpha plus beta solid. So as a whole, if we are observing the number of phases existing in this particular phase diagram, we can say a single phase liquid exists over a particular temperature range throughout at the higher temperature. There are two single phase solids existing. One is alpha single phase solid, it existing at a particular temperature range, which is a solid solution of copper in silver. And another single phase solid solution exists at the extreme right position, which is a solid solution of silver in copper. So two single phase solid solution is existing, and one two phase solid solution is existing over a very entire range, which is alpha plus beta solid solution. And there are region in which alpha plus liquid state existing, in which one single phase solid solution plus one single phase liquid solution exists. And there is another region where beta plus liquid, it is also a two phase region where one is liquid phase and another one is solid. That two phases exist at the region where this transformation from liquid to solid takes place. It is similar as in case of the isomorphous diagram. So three single phase solid solution exist: alpha phase, beta phase and liquid phase. Three two phase regions exist: alpha plus liquid, beta plus liquid and alpha plus beta, where alpha plus beta is the two phase solid solution. All the other twos are solid solution plus liquid solution. So another example for a eutectic system with limited solubility is lead-tin phase diagram. In the lead-tin phase diagram, similar to the silver copper phase diagram, we can observe an alpha phase, a beta phase with limited solubility, and in this case we can observe the eutectic point exists at 183 degrees centigrade and 61.9 percentage of tin. So as similar to the previous phase diagram, we can construct this phase diagram where extreme left position represents 100% lead, extreme right position represents 100% tin, and the weight percentage of tin is varying in the x-axis. Y-axis represents the temperature. Melting point of lead, it is 327 degrees centigrade. It starts from there, and the at the right side we'll be marking the melting point of the tin, which is 232 degrees centigrade. The eutectic point is marked at 183 degrees centigrade, and the eutectic composition, it exists at 61.9% of tin. The rest is similar to the previous case. We'll be having liquid phase, complete liquid phase existing at the higher temperature, and single phase solid existing at of tin dissolved in lead exists at the alpha region, and the single phase solid solution of lead dissolved in tin exists in the beta region. The two phase solid solution of alpha plus beta exists over the entire region in the below the eutectic point on in all other regions. So next we will discuss certain terms which is associated with this eutectic phase diagram. We already discussed the liquidus line. Liquidus line is the boundary which separate the liquid region from the region of liquid plus solid. So we will be having liquidus line above, which is the boundary, which is boundary of the separation, and the solubility limit, which we say the maximum solubility limit, that line, the line AB as well as line EF, that determines the boundary of the single phase region at left side as well as the right side. That particular boundary we normally call it as Solvest line, and the point at which this eutectic transformation takes place, we will call it as a eutectic point. The composition of the eutectic point, we will call it as eutectic composition. The temperature of eutectic point, we will call it as eutectic isotherm. Okay, and the composition of the alloys, which is towards the left side to the eutectic point, we can call it as hyper-eutectic composition, and the composition of the alloys towards the right side of the eutectic composition, we will call it as hyper-eutectic composition. These terms are very important. We will be dealing with these terms in detail in the iron carbon phase diagrams and the upcoming phase diagrams also. So the composition of the composition at eutectic point, we will call it as eutectic composition. The composition less than eutectic composition or towards the left of the eutectic composition, we will call it as hyper-eutectic composition. The composition which is higher than eutectic composition or towards the right of the eutectic composition, we will call it as hyper-eutectic composition. Okay. And the regions of the limited solubility at both left side as well as right side, which is the alpha solid solution as well as the beta solid solution, that particular limited solid solubility region we will be calling it as terminal solid solution. Okay. So next we will discuss about the evolution of the microstructure, how this microstructure is getting evolved when it is passing through different stages in a phase diagram, especially in the case of eutectic phase diagram. So for that we will have provided a schematic in which we can see we have marked three regions, which is highlighted as small green color, small green dots. We can see the first point we have marked inside a liquid region, in which we can see in the microscopic scale it will be completely has a single phase liquid region, which is marked as a blue color. When we are cooling it downwards, okay, when we are cooling it downwards at that particular composition, we can see we are only varying the temperature is lowered but the composition remains same. It will be transferred from a liquid phase region into the liquid plus solid phase region. So we can see we'll be having a liquid phase in which we'll be having small solid phases, so which is marked as the second point in the phase diagram. And if we are again cooling it to a much lower temperature, we can see from the liquid plus solid state it is transformed to a complete single phase solid, which is the alpha solid region. So inside the alpha solid region, we can see it will exist as a single phase solid solution. Even it have the composition of both phase, which is both elements, which is the element A as well as the element B, it will be a single phase solid solution. Okay, so this represents the evolution of the microstructure as a three stage when we are passing through a terminal solid solution. So terminal solid solution is the solid solution which is alpha or beta, which is having a limited solubility. When the terminal solid solution is formed, we can see it exists as a single phase solid solution. Similarly, now we are considering another composition in which we are constructing a cooling curve, and we are cooling the material at a fixed composition such that it passes through the terminal solid solution, but it is again cooled below such that it against a two-phase region or eutectic region. So here at starting point we can see it is single phase liquid. At a lower temperature we can see the liquid, it is transformed to liquid plus solid phase, in which we can see the liquid phase and the solid particles. Again upon solidification we can see it enters the alpha solid solution region, where the microstructural composition will be a single phase solid, but when we are again cooling it below, it will be unstable at that particular phase, and we can see at a lower temperature we can see the second phase will be precipitating, and at the end, at the last point, we can see it will be having the concentration of the two phases, the alpha phase as well as the beta phase. So when we discuss the solubility limit, we have seen the fact that the solubility limit is very much dependent upon the temperature. As the temperature increases, the solubility limit is increasing. So this is one very good example. We can see in alpha region at higher temperature, we can see there is a good solubility of B in A, but at a lower temperature, at the last point we can see there is a limited solubility of B in A. So the excess material of B will be precipitated as a separate phase. That's why we have a two phase at the final stage. Okay. Next is the microscopic evolution or the microstructure evolution when we are directly cooling the material at the eutectic point. You can see above the eutectic point it exists as a single phase liquid structure, and below the eutectic point it does not have a further transformation. It directly transforms to a two-phase solid. So we can see the traces of alpha and as well as the traces of beta. So it is a two-phase eutectic phase which exists below the eutectic point. Anywhere below the eutectic point it will be existing as a two-phase solid solution. So in the next class we can discuss the second classification of the eutectic phase diagram, which is the solid solution with complete solubility at liquid state and no solubility at the solid state. Okay, thank you.